Welcome to the Deep Dive. You're here because you want to get smart fast.
And we're here to help you do just that.
So let's jump right in. Today, it's all about aircraft systems. Think of this as your accelerated course on, well, the fundamental bits and pieces that let airplanes fly.
Exactly. We're looking at a great set of materials today. Covers everything from the engine, the heart of the machine, really, all the way through to the systems that keep things safe and comfortable upstairs.
We'll kick off with the power plant, looking at both reciprocating and turbine engines. Then we'll get into propellers, how that power actually moves the aircraft.
And induction systems, how the engine breathes.
Yep. And ignition, fuel, lubrication, cooling, all absolutely vital.
Can't forget those.
We'll also cover the electrical side, landing gear, and even the environmental controls that make high-altitude flight possible, even comfortable.
Our mission here isn't to turn you into an aircraft mechanic overnight.
No, definitely not.
But we do want to pull out the really important ideas behind each system, give you a clear, solid understanding without, drowning you in technical terms.
Okay, let's get started with the power plant. This is where the thrust comes from, the force that gets us moving and ultimately flying. Our sources really break this down into two main camps: reciprocating engines and turbine engines.
That's the core distinction. Reciprocating engines are what you find in, well, the vast majority of smaller planes. They work by turning chemical energy from fuel into mechanical energy.
Through pistons moving back and forth, right? Like tiny controlled explosions.
Precisely. Just like in many cars, really. Pushing pistons, turning a crankshaft.
And we're not talking about ancient technology here, are we? The materials mention some serious upgrades.
Oh, absolutely. Modern materials and, importantly, computerized engine management systems, think FADC, which we'll get to, have made a huge difference.
Better fuel efficiency.
Definitely. Better efficiency, cleaner running, and they've actually reduced the pilot's workload in managing the engine, too.
Okay, let's dig a bit deeper. Two main designs for these reciprocating types: spark ignition and compression ignition. Spark ignition is the old, reliable.
It is. It's been the standard in general aviation for decades. You mix fuel and air together. First, that's your fuel-air mixture, a specific ratio by weight.
Gotcha.
Then a spark plug ignites that mixture in the cylinder. A very precisely timed spark pushes the piston down.
And compression ignition. That's the alternative focused on lower costs.
Yeah.
How does that work without a spark?
It's a different philosophy. Instead of a spark, you compress the air in the cylinder incredibly tightly.
Right.
That compression generates intense heat. Then you inject the fuel, often diesel or jet fuel, directly into that super hot compressed air.
And it just ignites on its own.
It spontaneously combusts from the heat and pressure. It's pretty elegant, really.
And a big advantage, as our sources point out, is using cheaper, more available fuels like diesel or Jet A. That must really help with running costs.
It can make a significant difference. But mechanically, the core parts, cylinders, pistons, crankshaft, they're pretty similar in both types. The big difference is just how you kick off that combustion.
Okay. The materials also classify reciprocating engines by how the cylinders are arranged: radial, inline, V-type, horizontally opposed. Quite a few options.
There are, and each has its pros and cons. Radial engines, cylinders in a circle around the crankshaft, huge in World War II.
Why was that?
Fantastic power-to-weight ratio. Lots of power for their size.
Then inline engines, I imagine those are simpler, maybe?
Structurally, yes. Very narrow front profile, which is good for aerodynamics.
Yeah.
But cooling the rear cylinders can be tricky, and they generally have a lower power-to-weight ratio that limits how big you can make them.
V-type, like in cars.
Similar idea. Cylinders in a V, more horsepower than an inline, still relatively compact up front.
But for most small planes we see today, it's the horizontally opposed engine that dominates. Why is that one so popular?
Well, the boxer engine, as it's sometimes called, cylinders opposing each other, it's become the standard for good reason. Always an even number of cylinders.
Right.
And critically, a really good power-to-weight ratio because the crankcase can be light and strong. Plus, that flat shape fits really well in the cowling, very streamlined, cuts down drag.
Our sources mention figures 7.1 and 7.2 here, which presumably show these layouts.
Yeah, if you can picture those, it really helps visualize how these engines are packaged differently.
Okay, so that's the arrangement. What about the operating cycle? Two-stroke versus four-stroke. What's the difference in how they complete their work?
The cycle is about how many piston movements or strokes it takes to do the whole job.
Mm-hmm.
Intake, compression, power, exhaust. A two-stroke engine does all four jobs in just two strokes.
Two strokes, up and down once.
Exactly. You get a power stroke every single revolution of the crankshaft. That means, generally, a higher power-to-weight ratio than a four-stroke of similar size.
Hmm.
Figure 7.3 shows this for a compression-ignition type.
Sounds incredibly efficient, so why aren't they everywhere?
Well, historically, they weren't as fuel efficient and had higher emissions.
Uh,
But modern designs, especially with things like direct fuel injection and using pressurized air to clear out the exhaust scavenging, they're tackling those issues, making them very competitive now. Figure 7.3 gives a good look at that fast cycle.
Interesting. And the four-stroke. That's the standard in most GA planes today, right?
That's the one most pilots are familiar with. Figure 7.4 shows the main parts, and 7.5 breaks down the cycle. 4 distinct strokes for one power cycle. First is intake. Piston goes down, intake valve opens, fuel-air mix gets sucked in like taking a breath.
Then compression.
Piston comes back up, valves closed, squeezing that mixture, really important for getting a good bang later.
And then the power stroke, the main event.
That's it. Spark plug fires, ignites the compressed mix, big pressure increase pushes the piston down hard, turning the crankshaft. That's the power.
And finally, got to get rid of the used stuff.
Exhaust stroke, exhaust valve opens, piston comes up again, pushes the burn gases out, clears the cylinder for the next cycle. Figure 7-5 shows those 4 steps clearly. Even at idle, this is happening hundreds of times a minute in each cylinder. And with multiple cylinders, the power strokes are timed for smooth rotation.
Now, the material mentions diesel-fueled reciprocating engines, specifically Thielert's work, bringing automotive diesel tech to planes.
That's a great summary. Thielert saw the potential. Big advantage, like we touched on with compression ignition, is that diesel and kerosene Jet A fuel are very similar.
So more fuel options.
More fuel independence, potentially higher reliability because diesels are pretty robust, lower fuel burn than gasoline engines, and yeah, potentially big cost savings.
And Thielert aircraft engines, TAE, weren't alone, right?
No, TAE was a pioneer, got their first certified diesel in 2001, which was huge. But others like SMA are also making jet-fueled piston engines now.
And you can find these in planes like the Diamond DA-40 and DA-42.
Right. The DA-42 is actually the first new aircraft designed with a diesel from the start. Big deal. And they're also retrofitting them into popular planes like Cessna 172s and Piper PA-28s.
Offering an upgrade path. And the source mentions FADEC as standard on these. We'll get more into FADEC later, but it sounds like it makes managing the engine much simpler.
Oh, absolutely. Single lever control, basically. And by 2007, these engines had already flown hundreds of thousands of hours. Shows they were really gaining traction.
Okay, let's switch from the engine itself to the propeller system, the thing that actually grabs the air and pushes the plane forward. Our notes call it a rotating airfoil, using the same aerodynamic principles as a wing.
That's the perfect way to think about it. A wing generates lift up. A propeller generates thrust forward. Same physics apply induced drag, stalls. It can all happen to a propeller blade, too.
And the amount of thrust depends on
the blade's airfoil shape, its angle of attack, how it meets the air, and how fast it's spinning, the RPM.
I remember reading propellers have a twist. They aren't just flat blades. Why that twist?
Ah, the twist is critical. It's all about getting uniform thrust along the blade. Look at figure 7.6. The blade angle changes from the hub out to the tip.
Okay. Why?
Because the tip of the propeller travels much faster than the part near the hub, right? Covers a bigger circle in the same amount of time. Figure 7.7 shows that speed difference.
Right. Makes sense.
So to keep the angle of attack relatively constant along the blade, you need a higher pitch, a steeper angle near the slow-moving hub, and a lower pitch near the fast-moving tip. This twist ensures the whole blade is working efficiently together. It's clever aerodynamics.
So a prop with the same angle all the way across would be pretty inefficient, especially as airspeed changes.
Terribly inefficient. As you speed up, the inner parts might even start creating drag while the outer tips could stall. So we have 2 main types to deal with this: fixed pitch and adjustable pitch.
Let's start with fixed pitch. The name says it all the angle is fixed, can't be changed.
Correct. Set at the factory. Good for one specific airspeed and RPM combo. It's always a compromise, between climb and cruise. But they're simple, light, and cheaper.
And there are subtypes, right? Climb props and cruise props.
Exactly. A climb prop has a lower pitch, lets the engine spin faster for more power during takeoff and climb. Better initial performance.
But less efficient for cruising fast.
Right. Higher RPM for the same speed, burns more fuel. A cruise prop has a higher pitch. Slower RPMs on takeoff, maybe a bit less performance there, but more efficient at cruise speeds. Lower RPM, better fuel economy, it depends what the plane is designed for.
And how does the prop connect to the engine's power?
Usually bolted right onto the crankshaft, so prop RPM equals engine RPM, or sometimes there's a reduction gearbox, so the prop can spin slower, often more efficiently than the engine itself.
With a fixed pitch prop, how does the pilot gauge engine power?
The tachometer is your main guide. That's figure 7 and 8, shows engine RPM, usually in hundreds. Green arc is the normal range.
So throttle controls RPM, which equals power.
Roughly, yes. Adjust the throttle, you adjust RPM and power. But remember, at higher altitudes, the air is thinner, so the same RPM produces less actual power.
Okay, fixed pitch. Simple, but a compromise. What about adjustable pitch? Sounds more flexible.
It is. Ground adjustable props came first. You could change the pitch, but only on the ground, engine off.
So you could optimize it for that specific flight's needs.
Exactly. Set a low pitch for lots of short field takeoffs, or a higher pitch for a long cross-country cruise. But you couldn't change it once airborne. Early ones just had 2 settings, high and low. Later ones had more range.
Which leads us to the constant speed propeller. That seems like the gold standard for adjustable pitch in smaller planes. How does that work?
It's a really smart system. It is an adjustable pitch prop, but the pitch changes automatically in flight. There's a device called a governor.
A governor.
Yeah, its job is to keep the engine RPM exactly where the pilot sets it, no matter if the plane speeds up, slows down, climbs, or descends. It automatically changes the blade pitch to maintain that RPM.
So it's always operating efficiently.
Much more efficiently across a wider range of speeds and conditions than a fixed pitch. It lets the pilot choose the best RPM for climb, cruise, whatever, and the prop adapts.
So in the cockpit, you have the throttle for power output and a separate propeller control for setting the RPM.
Precisely. You set the desired RPM with the prop control, and the governor handles the rest. Plane speeds up, governor increases the pitch, takes a bigger bite of air, keeps RPM from rising, plane slows down or climbs. Governor decreases pitch, takes a smaller bite, keeps RPM from dropping.
The material mentions a constant speed range. What's that?
That's just the range of blade angles the prop mechanism can physically achieve between its high-pitch stop and low-pitch stop.
Okay.
As long as the governor needs an angle within that range to hold the set RPM, it works perfectly. But if things change so much that the blades hit either the low-pitch limit, like at very slow speeds, or the high-pitch limit at very high speeds, the governor can't adjust further.
So then it acts like a fixed pitch prop again.
Essentially, yes. At that point, the RPM will start to change with airspeed, just like a fixed pitch.
Now, if the tachometer isn't the main power indicator with a constant speed prop, what gauge do pilots watch?
That would be the manifold pressure gauge, or MAP gauge. Figure 7.9 shows one. It measures the absolute pressure of the fuel-air mixture inside the intake manifold just before it goes into the cylinders.
So higher pressure means more mixture going in, more potential power.
Exactly. At a given RPM and altitude, power is pretty much directly related to manifold pressure. Open the throttle, more mixture flows, MAP reading goes up.
Our notes have some interesting MAP readings. Engine off at sea level, it reads atmospheric pressure, around 29.92 inches of mercury.
Correct. And when the engine's idling, the MAP drops way down.
Why is that?
Because the throttle is mostly closed, restricting airflow, and the pistons are creating suction, a partial vacuum, in the manifold. Interestingly, MAP can also hint at engine failure. If the engine quits, the MAP will usually rise back towards the ambient atmospheric pressure for that altitude.
And, like the TACH, the MAP gauge has color markings too.
Yep. Green arc for the normal operating range, red line for the absolute maximum you should never exceed.
Okay.
And it's really crucial not to run a high manifold pressure with a low RPM setting. That can seriously overstress the engine cylinders.
So there's a specific order for changing power settings with these props.
Absolutely vital. When decreasing power, reduce MAP first, throttle back, then reduce RPM, prop control back. If you reduce RPM first, the governor might increase the pitch, which could spike the MAP over the limit.
And increasing power.
Opposite order. Increase RPM first, prop control forward, then increase MAP, throttle forward. Follow that sequence, keep the engine happy. The notes also mention some specific cautions for older radial engines about RPM and MAP combinations.
The material even mentions propeller overspeed and an FAA bulletin about it. What's the concern there?
Propeller overspeed is when the prop spins faster than its maximum safe limit. The FAA bulletin highlights that pilots need to react correctly if this happens with a variable pitch prop. Interestingly, in some glide situations, slowing below the best glide speed might actually increase the thrust from an overspeeding prop if it's hit its low pitch stop. Makes it hard to descend properly.
Counterintuitive.
Yeah, it means the published best glide speed might not always be the best speed to manage an overspeed. Depends on the specific aircraft and prop. Something pilots need to be aware of.
Okay, engine power, propeller thrust. Now let's talk about how the engine breathes, the induction system.
Right. Its job is simple but critical. Bring in outside air, mix it with fuel, usually, and deliver that mix to the cylinders for burning.
Air comes in through an intake at the front, usually filtered.
Yep, behind the prop, typically. There's an air filter to keep out dust, bugs, you name it.
And if that filter gets clogged, say, with ice.
Gotta have a backup.
Oh.
An alternate air source is essential. Usually pulls unfiltered air from inside the engine cowling, bypassing the main filter. Can be automatic or manual.
Okay, and the big split here is how fuel gets mixed in, carburetor or fuel injection. Let's tackle carburetors first, still common on smaller planes.
Very common. Two main types. Float type, which is the most common on small aircraft, and pressure type, which is less common. Float types have lots of little subsystems for different operating conditions, idling, acceleration, mixture control, etc.
And the difference is how the fuel gets delivered.
Fundamentally, yes. Float types rely on air pressure differences to draw fuel in. Pressure types use a fuel pump to push fuel in under pressure.
Can you walk us through how a basic float type carburetor works?
Sure. Fuel comes into a little bowl, the flute chamber. A float sits on the fuel.
Like in a toilet tank.
Exactly the same principle. As the fuel level changes, the float moves a needle valve, controlling how much fuel comes in, keeping the level pretty constant. Meanwhile, air rushes in through an intake and gets squeezed through a narrow section called a venturi.
Like pinching a garden hose.
Precisely. Air speeds up, pressure drops. That low pressure in the venturi sucks fuel out of a tiny nozzle placed right there. Fuel and air mix then get drawn into the engine. The throttle plate, controlled by the pilot's throttle lever, regulates how much of that mixture gets through.
Sounds straightforward, but the notes mention downsides, especially icing.
Yeah, flute carbs aren't perfect. Sloshing fuel in maneuvers can upset the mixture. Vaporization isn't always complete. But the big one, the main disadvantage, is their tendency to ice up.
Carburetor icing. What causes it exactly? It sounds like it can happen even above freezing.
It can, and that's the sneaky part. Two things make the inside of the carb very cold. Fuel vaporizing absorbs heat, and the air pressure dropping in the venturi cools it down further.
Okay.
If there's moisture in the air, and the temperature inside the carb drops to freezing or below, bam, ice forms, usually right on the throttle valve or in the venturi throat. Figure 711 shows where.
And that blocks the airflow.
Exactly. Restricts the mixture, reduces power, and can even stop the engine completely.
And it can happen even if it's, say, 70 degrees Fahrenheit outside.
Absolutely. It's most likely below 70 F 21C with high humidity over 80%, like shown in figure 712. But that temperature drop inside can be huge, 60, 70 degrees F sometimes. So you can get ice even at 100 F 38C if it's humid enough. The way float carbs discharge fuel low pressure right where it's coldest makes them prone to this.
Now, pressure-type carbs are less likely to ice up.
Much less. They inject fuel under pressure after the throttle valve. So the main vaporization cooling happens downstream where it's less likely to cause ice. Plus, they handle maneuvers better since the fuel chambers stay full.
Another key part of induction is mixture control.
Right.
Why does the pilot need to adjust the fuel-air ratio?
It's crucial for efficiency and engine health. As you climb, air gets thinner. If you don't lean the mixture, reduce fuel flow, it becomes too rich.
All right.
Conversely, the source specifically notes that during descent into denser air, if you don't enrich in the mixture, it can become too lean. And a lean mixture burns too hot, risking detonation. That uncontrolled, damaging explosion in the cylinder causes roughness, overheating, power loss.
So how do you manage it?
Monitoring engine temps is key. EGT, exhaust gas temperature, is the best tool for fuel-injected engines. But always follow the specific procedures in the AFM or POH for your aircraft.
And to fight carb ice directly, there's carburetor heat.
Yep, an anti-icing system. It routes hot air, usually heated by the exhaust manifold, into the carb intake before the venturi.
Warms things up to prevent ice or melt existing ice.
Both. Best used preventatively if you suspect icing conditions. It can melt some ice, but not if it's too thick. It also often acts as the alternate air source if the main filter blocks. You always check carb heat during the run-up.
But using carb heat affects performance, doesn't it?
It does. That hot air is less dense, so engine power drops maybe up to 15%, and it enriches the mixture.
How does it show up in the cockpit if you have ice?
Fixed pitch prop. RPM drops initially, then might gradually rise as ice melts. No ice. RPM just drops and stays down. Constant speed prop, manifold pressure drops, then might gradually rise as ice melts. No ice. MEP drops, and the rise isn't obvious until you turn the heat off.
So recognizing the signs is key.
What are they again? Fixed pitch. Unexplained drop in RPM, maybe roughness. Constant speed. Unexplained drop in manifold pressure, maybe roughness.
In the immediate action.
Full carburetor heat. Right away. Expect it might run rougher for a moment as the melted ice goes through. Don't turn it off too soon. Keep it on until you get normal power back.
Some planes have a carb air temp gauge.
Yes, a CCAT gauge. Often has a yellow arc, maybe galactic 15 to +5 Celsius, where icing is most likely. See figure 712 again. If conditions are right, you use carb heat to keep the needle out of that yellow arc. Might also have red max temp line, green normal range. And the outside air temp OAT gauge helps assess the risk too.
Okay, carburetor's covered. Let's switch to fuel injection systems. How do they work differently?
Instead of mixing fuel and air in a carburetor, fuel injection sprays fuel directly into the cylinders or right into the intake port just before the valve.
Still needs air, though. Same intake system.
Pretty much. Filtered air intake, alternate air source inside the cowling, often automatic with a manual backup.
And the key fuel injection components.
Yeah.
Figure 713 shows them.
Right. You've got an engine-driven fuel pump for normal operation, a fuel air control unit that meters the fuel based on throttle and mixture settings, kind of replaces the carb, a fuel manifold or distributor to send fuel to each cylinder.
Okay.
Discharge nozzles, the injectors themselves, in each cylinder head, an auxiliary electric fuel pump for starting and backup, and fuel pressure flow gauges in the cockpit.
So the O-pump gets it started, then the engine-driven pump takes over.
Usually, yes. The control unit meters fuel, sends it to the manifold, which distributes it evenly to the nozzles for injection.
And less susceptible to icing than carbs.
Much less susceptible to fuel vaporization icing because there's no Venturi cooling effect in the same way. But importantly, the air intake can still get impact ice, just like on a carbureted engine. That can still choke the engine.
What are the big advantages of fuel injection then?
Besides less icing risk, better fuel flow control, faster throttle response, more precise mixture control across all cylinders, better fuel distribution, and often easier cold starts.
Any downsides?
Yeah, a few. Hot starts can sometimes be tricky. Think vapor lock in hot fuel lines.
Vapor lock, fuel boiling in the lines.
Essentially, yes. Can happen on hot days on the ground, too. And restarting after running a tank dry can sometimes be harder than with a car, getting the air purged out.
Okay, we know how air gets in and mixes with fuel. What about boosting engine power with superchargers and turbo superchargers?
Forced induction. Both systems cram more air into the engine than it could suck in naturally. More air means you can burn more fuel, means more power.
How do they do that? Compression.
Exactly. They compress the intake air, increasing its density.
What's the key difference between a supercharger and a turbo?
How they're powered. A supercharger is mechanically driven by the engine gears, belts, takes some engine power to run. A turbocharger uses the engine's exhaust gas energy to spin the compressor. It recycles waste energy.
Both use a MAP gauge to show the boost pressure.
Right. And remember, engine off at sea level MAP shows atmospheric pressure about 29.92 inches. It decreases as you go up.
And normally, aspirated engines lose power as they climb because of that decreasing pressure hitting a service ceiling. How do super turbochargers help?
By forcing compressed air in, they maintain higher manifold pressure at altitude, lets the engine keep making power much higher up, increases service ceiling, allows higher true airspeeds, lets you fly over bad weather.
Let's look at superchargers first, driven by the engine itself.
Correct. An engine-driven air pump boosting intake pressure lets the engine get MAP above normal atmospheric pressure, often over 30 inches Hg.
Can you give an example?
Sure. A normally aspirated engine might lose 25% of its power by 8,000 feet. A supercharger might allow it to maintain sea level MAP or close to it at that altitude. The benefit is even bigger at, say, 18,000 feet where air density is halved. A supercharger can make it feel like sea level to the engine.
And the components, similar to normally aspirated plus the supercharger unit.
Pretty much. The supercharger sits between the fuel metering device, carb injector, and the intake manifold. Driven by gears, could be single speed, two-speed, even variable speed, single or multiple stages of compression.
The notes mention sea level and two-speed superchargers. Differences.
A basic sea level supercharger, single stage, single speed, boosts power at all altitudes, but power still drops off as you climb. A two-speed supercharger, common on big ol' radial engines, had a low blower setting for takeoff, ground-boosted power drops with altitude, and a high blower setting the pilot engaged at a certain altitude. That made it an altitude engine, maintaining power higher up. Figure 714 compares them. usually in oil pressure clutch switched speeds.
Okay, now turbo superchargers, turbochargers. Generally more efficient, you said.
Definitely. Because they use exhaust energy, they don't rob crankshaft power like a supercharger does. That's a huge efficiency gain.
And another advantage for high altitude.
Yes, they can maintain the engine's rated sea-level horsepower all the way up to the critical altitude.
Critical altitude.
That's the max altitude where the turbo can still deliver enough boost to maintain full rated power. Above that critical altitude, power starts to drop off like a normally aspirated engine. Figure 715 shows the turbo setup.
How does a turbo actually work?
Two main parts on one shaft, a turbine wheel and a compressor impeller. Hot exhaust gas spins the turbine.
Okay.
The turbine's connected to the compressor impeller, which spins really fast, sucking in outside air, compressing it, and forcing it into the engine intake. More dense air, more power.
And there's a wastegate.
Crucial part. It's a valve in the exhaust pipe before the turbine. It controls how much exhaust gas actually goes through the turbine versus bypassing it. Close the wastegate, more exhaust hits the turbine, spins faster, more boost. Open it, less exhaust hits the turbine, less boost. It's how you regulate the MAP.
I also see intercooler mentioned. What's that for?
Compressing air makes it hot. Hot air is less dense and also increases the risk of detonation. An intercooler is like a radiator for the intake air. It cools the hot compressed air coming from the turbo before it goes into the engine. Cooler, denser air means even more power potential and less detonation risk.
How is the wastegate controlled? Does the pilot manage it directly?
On most modern GA turbos, it's automatic. A pressure sensor measures MAP and tells an actuator, often using engine oil pressure, how much to open or close the wastegate to maintain the MAP the pilot selects with the throttle.
So it's pretty hands-off.
Mostly. Some older systems or aftermarket ones might have manual wastegate control. That requires constant pilot attention. Leave it closed during a descent, and as air density increases, you could easily overboost exceed max MAP limits. Very dangerous, can cause severe detonation.
Even automatic systems aren't foolproof.
Not entirely. Applying takeoff power too quickly with cold, thick oil might delay the wastegate opening properly, causing a temporary overboost. Smooth throttle application is key.
Any other turbo-specific things pilots need to watch?
Yes. Turbos spin incredibly fast and get very hot. Reliable oil supply for cooling and lubrication is critical. Always let oil temp get into the green arc before demanding high power.
And cool down time after landing.
Highly recommended. Let the engine idle for a bit before shutdown, allows the hot turbine to slow down and cool gradually, prevents oil from coking or baking onto the bearings, which kills performance and lifespan. Always check the AFM-POH for specific procedures.
And monitoring MAP during climb in a turbo. What should you see?
As you climb, the automatic wastegate should gradually close to maintain max MAP. When you reach critical altitude, the wastegate will be fully closed. Climb higher, and MAP will start to drop because the turbo just can't compensate anymore.
What if MAP starts dropping before critical altitude?
That suggests a problem. Either the engine isn't making expected power, or the turbo system isn't delivering the boost it should. Time for a mechanic to take a look.
Okay, we've got air in, boosted it, mixed it with fuel. Now we need to light the fire. The ignition system in spark ignition engines.
Right. Its job is simple. Deliver a spark at the right time. Key parts, shown in figure 716, magnetos, spark plugs, high-tension leads, wires, and the ignition switch.
The magneto, that's the heart of it.
It is. It's a self-contained generator. Uses a permanent magnet and engine rotation to create high voltage for the plugs. Crucially, it's independent of the aircraft's main electrical system.
So even if the battery dies, the engine keeps running.
As long as the engine is turning, the mags are making sparks. Starts firing as soon as the starter turns the engine. Keeps going as long as it runs.
And most planes have two magnetos. Dual ignition.
Yep. Two separate mags, each firing its own set of spark plugs, usually one plug per mag in each cylinder. Huge safety benefit redundancy.
If one mag fails, the other keeps the engine going.
Exactly. You'll get a slight power decrease, but the engine runs. Plus, firing two plugs gives slightly better, more complete combustion. A small power boost and smoother running.
And the ignition switch controls which mags are active.
Correct. Usually 5 positions. O off F, R, right mag only, L, left mag only, both mags active, and start engage a starter usually activates both mags.
There's a pre-takeoff check involving that switch.
Right, absolutely essential. During the run-up, you switch from both to R, check for a slight RPM drop, then back to both, then to L, check for a slight drop again.
What does that tell you?
A small expected RPM drop, specified in the POH, shows each mag is working. If the engine quits or the drop is excessive, you've got a problem. Fouled plugs, bad wire, bad timing, don't fly. Interestingly, no RPM drop is also a problem, might mean a grounding issue.
And after shutdown, always turn the switch to O off F.
Critically important safety item. If you leave the switch on N and someone moves the propeller, the mags could generate a spark, and if there's any fuel left, the engine could fire. Mags need no battery power.
And what if the ground wire to the magneto is broken?
Even more dangerous. Then the mag is hot even if the switch is O off F. Moving the prop could start the engine unexpectedly. If that happens, only way to stop it is mixture to idle cutoff, then get it fixed immediately.
Okay, moving parts need lubrication. Let's talk oil systems.
Oil does a lot more than just lubricate, though that's key. It reduces friction, definitely. But it also cools internal parts by carrying heat away, especially from the pistons and cylinders.
What else?
It helps seal the piston rings against the cylinder walls for good compression, and it cleans, carrying away tiny bits of metal wear and combustion byproducts to the filter.
Two main types of systems, wet sump and dry sump.
Right. Wet sump, shown in figure 717, is most common in smaller engines. The oil supply is stored in the sump, which is part of the engine crankcase itself. Pump draws oil from there, circulates it, and it drains back. Simple. Some might use crankshaft splashing, too.
And dry sump?
That's for larger engines usually, or aerobatic ones. The oil is stored in a separate tank external to the engine. A pressure pump sends oil from the tank to the engine, and then scavenge pumps collect the oil from various points in the engine and pump it back to the tank. Allows for a larger oil supply and better lubrication during maneuvers.
Cockpit instruments for oil. Pressure and temperature gauges.
Yep. Oil pressure gauge shows psi, direct indication of system health. Green arc for normal, red lines for min-max. Should show pressure right after start. Always check POH limits.
And temperature.
Oil temp gauge. Also green arc, red line for max temp. Changes slower than pressure. Keep an eye on it, especially in extreme temps. High temp could mean low oil, plugged line, blocked cooler, bad gauge. Low temp might mean wrong oil viscosity for cold weather.
And the pre-flight check involves the dipstick.
Always. Figure 718 shows a typical access. Check the level, add oil if needed, use the exact type and weight specified in the POH or on placards. Check min-max quantity lines.
Okay, lubrication covered. Engines get hot. Let's talk cooling systems.
Burning fuel creates intense heat. You have to get rid of it. Overheating leads to power loss, high oil consumption, detonation, and serious damage scored cylinders. Ruined pistons and rings, warped valves, bad news.
Most light aircraft engines are air-cooled, right? Like figure 719.
Correct. Liquid cooling is rare in GA. Air cooling relies on outside air flowing over the engine. Air comes in the cowling front, baffles directed over the hot parts, especially the cylinders which have fins to increase surface area.
Like cooling fins on a motorcycle engine.
Exactly the same principle, but it's less effective on the ground or during high-power, low airspeed climbs. Not as much airflow. Conversely, a fast descent can cause shock cooling too rapidly, which isn't good either.
How do pilots monitor engine temperature?
Oil temp gives an indirect, slow indication. The main one is the cylinder head temperature gauge, CHT. Measures temp directly at one or more cylinder heads. Much faster response. Calibrated in C or F, green arc for normal, red line for max temp.
If CHT gets too high, what can the pilot do?
Several things. Increase airspeed to get more cooling air. Enrich in the mixture, which has a cooling effect. Reduce power setting. And if the aircraft has cowl flaps,
Cowl flap.
adjustable vents at the back of the cowling, open them up to let more air flow through and cool the engine. Close them down in cruise or cold weather to help the engine warm up or stay warm.
We can't forget where the burn gases go. Exhaust systems.
Right. Main job, get the burned gases out safely. But they often do double duty, providing heat for the cabin and for defrosting the windshield.
Component.
Exhaust pipes from each cylinder, usually leading to a muffler to reduce noise, and often a shroud around the muffler for heating.
How does the cabin heat part work?
Outside air is ducted through that shroud around the hot muffler. It picks up heat, then this hot air is piped into the cabin. Pilot controls the flow.
And the big danger with exhaust systems is
Carbon monoxide, CO. It's odorless, colorless, deadly. The exhaust system must be in perfect shape, no cracks or leaks, to prevent CO from getting into the cabin heat supply and poisoning the occupants. Regular inspections are critical.
Some exhaust systems have an EGT probe too. We mentioned this for mixture.
Yep, exhaust gas temperature probe. Measures temp right at the exhaust manifold. Since EGT varies directly with the fuel-air ratio, it's the primary tool for leaning the mixture accurately for best fuel economy, especially in fuel-injected engines. Always follow the manufacturer's specific leaning procedure.
Okay, systems covered. How do we get the engine started in the first place? The starting system.
Most small planes use an electric starter. Needs a power source, battery or external power, wiring, switches, a solenoid, and the starter motor itself. Figure 720 shows a typical circuit. Some really old planes might have mechanical starters.
How does the electric starter work?
Pilot hits the start switch. That energizes the starter solenoid, which is like a heavy-duty relay.
Okay.
The solenoid connects the high current from the battery to the starter motor. The motor spins a small gear that engages with a large ring gear on the engine's flywheel.
So the little motor turns the big engine.
Exactly. Cranks the engine over. Once the engine fires and starts running on its own, the starter gear automatically disengages, usually with an overrunning clutch, so the engine doesn't spin the starter motor too fast.
Safety during starting is paramount.
Absolutely. Prop clear. Check. Wheels chalked. Check. Brake set. Check. Area clear of debris. Check. Propeller blast is powerful.
We've talked about normal combustion. What about abnormal combustion, detonation, and pre-ignition?
Right. Normal combustion, shown in figure 721, is a smooth, controlled burn starting at the spark plug. Detonation is different. It's an uncontrolled, explosive ignition of the remaining fuel-air mixture after normal ignition has started.
Like a secondary explosion.
Kind of.
Yeah.
Creates sudden, extreme spikes in temperature and pressure. Very damaging, can wreck pistons, cylinders, valves. Even mild detonation causes overheating, roughness, power loss.
And pre-ignition.
That's when the mixture lights off before the spark plug fires. Usually caused by a hot spot in the cylinder, maybe a glowing carbon deposit, a cracked spark plug insulator, something like that.
Well,
very bad. Causes power loss, high temps, and can destroy the engine because it puts pressure on the piston while it's still coming up on the compression stroke.
can they happen together? And how do you avoid them?
They can happen together, and it's hard to tell which is which, as both cause high temps and poor performance. Best prevention: use the correct fuel grade, always, and operate the engine within its recommended temperature, pressure, and RPM limits. Don't push it too hard, basically.
Now, a big leap forward in engine management, FADC. Full authority, digital engine control.
Yes, this is a game changer. A computer system with sensors that manages the engine and sometimes the propeller, too. Started in turbines, now increasingly used in piston engines.
How does it work on a piston engine?
It monitors everything's speed, temp, pressure for each cylinder. Then the computer calculates the perfect fuel injector pulse and ignition timing for optimal performance, constantly adjusting. Similar idea for compression ignition, just without the spark timing aspect.
So it replaces a lot of traditional controls.
Absolutely.
Yeah.
No magnetos needed. Electronic ignition. No carb heat. Mixture is precisely controlled. No manual mixture lever. No priming needed. Often just a single power lever for the pilot. Select start, idle, cruise, max power, and FADEC figures out the engine and prop settings automatically. Pilot doesn't worry about leaning the mixture.
Handle starting too.
Yep. Primes, sets mixture, positions throttle based on temps and pressures. And in cruise, it's constantly fine-tuning fuel flow and ignition timing for each cylinder. Often gives better fuel economy and more horsepower than a traditional setup.
Since it's so critical, what about failures?
Huge focus on redundancy. FADEC is usually powered by the aircraft electrical system or its own dedicated generator, always has a backup power source, and critically, FADEC systems almost always have two completely separate, identical digital channels. If one fails, the other takes over instantly. Very reliable.
Okay, let's completely shift gears now to turbine engines. Powering jets and turboprops.
Right. Fundamentally different. Basic parts: air inlet, compressor, combustion chambers, turbine section, exhaust. Thrust comes from accelerating air to high velocity.
Advantages.
Very smooth, high power-to-weight ratio, use jet fuel. Historically too expensive for small planes, but advances are making them viable for very light jets, VLJs, or microjets. Figure 722 shows an example.
How are turbines classified? Compressor type first.
3 main compressor types: centrifugal flow, air thrown outwards; axial flow, air pushed straight back through stages of blades; and centrifugal axial, a mix. Figure 727 shows a dual spool axial flow.
And classified about how they produce power. Turbojet, turboprop, turbofan, turboshaft.
Exactly. A turbojet, figure 723, is the simplest. Compressor, combustor, turbine, driving the compressor, exhaust. Thrust comes purely from the high-speed exhaust gas. Basic jet engine. Can be inefficient at lower speeds, slow throttle response sometimes.
Turboprop, figure 724.
Uses the turbine core to drive a propeller through a reduction gearbox. Props need to spin much slower than the turbine.
So most thrust from the prop.
Yes, vast majority from the prop, some residual from the exhaust. Good compromise between jet speed and piston efficiency. Best around 250, 400 mile per hour, 18,000, 30,000 feet. Good takeoff performance, fuel efficiency in that range.
Turbofan, figure 725, mixes jet and prop ideas.
Kind of. Has a large fan at the front. Some air goes through the core engine like a turbojet, but a lot of air bypasses the core and just gets accelerated by the fan.
Why bypass?
Increases total thrust, improves efficiency, cools the engine, and makes it much quieter than a pure turbojet. Gives jet-like speeds with better fuel economy. The ratio of bypass air to core air, the bypass ratio, is a key design factor.
And turbo shaft, figure 726, for helicopters.
Mostly, yes. Designed to deliver power to a shaft, not produce thrust directly, that shaft drives the helicopter rotors or maybe an auxiliary power unit, APU, on a big plane. Most turbine energy goes to turning the shaft, not making jet exhaust.
Turbine engine instruments. Some overlap with pistons, some unique.
Right. You still have oil pressure temp, engine speed, often percent RPM, EGT, fuel flow. Unique ones include engine pressure ratio, EPR, turbine discharge pressure, and torque meter, and multiple temp sensors in the hot section.
EPR, engine pressure ratio, what's that for?
Primary power indicator for turbojets turbofans. It's the ratio of exhaust pressure to inlet pressure. Measures how much the engine is boosting the air pressure, automatically compensates for speed altitude, but might need temp correction.
EGT, exhaust gas temperature. Still critical.
Absolutely. Turbine temperature is a major limiting factor. EGT, TIT, turbine inlet temp, TOT, turbine outlet temp, ITT, interstage turbine temp. Different names, but all measure temps in the hot section to prevent melting the turbine blades.
Torquemeter, for turboprops and turboshafts.
Yes. Measures the twisting force, the torque, being delivered to the output shaft. That's the real measure of power for those engines, usually shown as percentage, foot-pounds, or pi.
Operational considerations for turbines. It sounds like there are a few key ones.
Definitely. Always respect temperature limits. Be extremely careful about foreign object damage, FOD. Know how to handle hot starts or hung starts. Understand compressor stalls, and be prepared for flameouts.
Temperature limits, TIT, usually the main one.
Often, yes. Exceeding it, even briefly, can cause serious damage.
Thrust varies with air density.
Directly. Less dense air, higher altitude, hotter temp, means less thrust. Interestingly, humidity affects turbines much less than pistons.
FOB, foreign object damage, sounds nasty.
It is. Turbine intakes suck in huge amounts of air. Any debris on the ground, rocks, tools, gravel can get ingested. Bird strikes, ice ingestion too, can destroy compressor and turbine blades. FOD prevention is a massive priority. Pre-flight inspection of intakes is vital.
Hot starts and hung starts during engine start.
Hot start is when EGT shoots past the limit during start, usually too much fuel for the airflow RPM, needs inspection after. Hung start is when the engine lights off but fails to accelerate to idle speed. Could be weak starter, fuel control issue.
Compressor stalls, figure 728, airflow disruption.
Exactly. Airflow breaks down in the compressor stages. Angle of attack on the compressor blades gets too high. Can be a momentary pop or bang, or a severe steady roar with vibration.
Indications.
Mild ones might not show. Developed stalls cause RPM fluctuations, EGT rise. Transient stalls might clear themselves. Steady stalls need immediate action. Reduce power, lower aircraft angle of attack, maybe increase airspeed. Most modern engines have anti-stall features, variable vanes. Follow POH procedures.
And flame out. Engine just quits burning.
Yes, unintentional loss of combustion. Can be too rich, rapid acceleration maybe, too lean, high altitude, throttled back, fuel interruption, maneuvers, system failure, turbulence, icing, running out of fuel. Symptoms like engine failure, air start might be possible if the cause is fixed. POH gives procedures and envelopes for restart.
The material compares performance too. Figure 729, what's the gist?
Generally shows pistons are best at low speeds, turboprops better than turbofans at medium speeds, turbofans better than turbojets there. As speed increases, turbofans overtake props, then jets overtake fans. Shows which engine type is best suited for different speed regimes based on thrust versus drag.
Okay, massive section on power plants, done. Let's move to other key airframe systems. Fuel, electrical, hydraulic, oxygen.
Right. All essential. Let's start with the airframe fuel system. Job is to get clean fuel from tanks to engine, always.
Two main types in small planes, gravity feed and fuel pump. Figure 730.
Correct. Gravity feed relies on gravity. Tanks higher than the engine, like in high-wing planes. Fuel flows down. Simple.
In fuel pump systems.
Needed when tanks are below the engine, like low-wing planes. Uses an engine-driven main pump plus an electric auxiliary or boost pump for starting a backup. Pilot controls the O-pump.
Fuel primer helps with starting.
Yes, especially when cold. It injects a little raw fuel directly into cylinders or manifold to help get combustion started. Bypasses the carb injector initially. Crucial to lock it off after starting. Or it could make the engine run way too rich. Follow POH priming instructions carefully, don't overprime.
Fuel tanks, usually in the wings.
Yeah.
Features.
Yep, filler cap on top.
Yeah.
Vented to allow air in as fuel is used, prevents vacuum. Overflow drain for fuel expansion on hot days. Seeing a little drip after fueling on a hot day is normal.
Fuel gauges in the cockpit. How reliable?
They show quantity, gallons or pounds, but legally they only have to be accurate when reading empty. Treat them as approximate. Always visually check tanks during pre-flight and cross-reference. Don't bet your life on the gauge reading alone. Fuel pump systems also have a pressure gauge.
Fuel selectors let the pilot choose tanks. Figure 731.
Right. Left, right, both off are common settings. Lets you manage fuel balance. Check placards for limitations like both for takeoff landing. Monitor consumption carefully. Running a tank dry is bad engine quits, creates imbalance, and can make restart hard due to air vapor in lines, especially with injection.
Strainers, sumps, drains for clean fuel.
Absolutely. Fuel goes through a strainer before the engine. Dirt and water
Pre-flight check.
critical. Drain each sump into a clear cup. Look for water. It'll bead or layer at the bottom, or dirt. If you find any, keep draining until it's perfectly clean fuel. Never fly with contaminated fuel. Know your specific aircraft's fuel system drains.
Fuel grades AVGAS. Octane rating is key.
Yes. Indicates resistance to detonation. Higher number, more resistance. Always use the grade specified in the POH placards. If unavailable, use the next higher grade, never lower. And never use autogas unless the plane has an FAA STC for it.
Current grades.
Mostly 100 LL, low lead, blue color. Older 100, green is rare. Grade 80, red is mostly gone. Turbine fuel, JTA, etc., is kerosene-based, clear or straw-colored, smells like kerosene. Color coding and decals, figure 732, help prevent misfueling. There's also a newer 100 VLL, very low lead, also blue, mentioned in an SAIB that's okay for engine certified for 80 up to 100 LL.
Fuel contamination, big cause of accidents. How to prevent.
Often due to poor pre-flight, bad filtering during refueling, water condensation in partially full tanks, poor maintenance. Prevention. Thorough sump draining before every flight. Fill tanks after flight to minimize condensation space. Avoid fueling from cans rooms if possible. If you must, use meticulous grounding and bonding procedures to prevent static sparks. Fuel fires are catastrophic. Chamois filters, risky for static, may not filter water well. Be careful.
Fuel system icing. Water freezing in the fuel lines.
Yes. Water can be suspended, entrained, or settled, free. Free water at the bottom is usually drainable. Entrained water can stay suspended, especially in cold AVGAS. If water freezes in lines or filters, it blocks fuel flow, can also make carb ice worse.
Prevention.
Anti-icing fuel additives can help lower the freezing point of water, but they are not a substitute for using carb heat correctly. Always follow carb heat procedures. Be vigilant during refueling.
Okay, let's warm up with heating systems.
Lots of types. Always check the specific aircraft manual.
Types mentioned. Fuel-fired, exhaust heat, combustion heaters, bleed air.
Right. Fuel-fired are like small furnaces burning aircraft fuel, need electricity for fans. Exhaust heat uses heat from the muffler shroud, common in light planes, but carries CO risk if exhaust leaks. Combustion heaters are more complex, burn fuel in a sealed chamber, heat ventilation air passing over it safer regarding CO. Bleed air systems use hot air tapped from turbine engine compressors. Each needs proper maintenance and checks.
Electrical system next. Powers almost everything else.
Usually 14 or 28 volt DC, main parts.
Yeah.
Alternator, generator, battery, master switch, bus bar, fuses, breakers, voltage regulator, ammeter or load meter, wiring.
Alternator generator makes power, battery stores it for starting and backup.
Exactly. Alternators work better at low RPM than older generators. Many planes have external power receptacles, GPU, for ground power starting.
Master switch controls most things. Figure 733.
Yep, often split into battery and alternator halves, turns on lights, radios, instruments, fuel pumps, etc. Everything except the engine ignition mags, usually. Some planes have separate alternator twitches too, to isolate a faulty one.
Bus bar is like a central power strip. Figure 734.
Good analogy. Simplifies wiring, distributes power.
Fuses and circuit breakers protect the circuits.
Yes, from overloads. Fuses blow and need replacing, carry spares. Breakers trip and can be reset, usually. Placards show circuit and amp rating.
How do pilots monitor the electrical system? Ammeter or load meter? Figure 735.
Ammeter shows current flow charging, plus or discharging the battery. Big deflection means trouble. Load meter shows total load drawn from alternator generator as a percentage of capacity. Voltage regulator keeps the voltage stable and controls battery charging. Needs to be slightly higher than battery voltage to charge it.
Hydraulic systems, what do they power?
Depends on the plane. Small planes, often wheel brakes, retractable gear, maybe constant speed props, larger planes, flight controls, flaps, spoilers, thrust reversers.
Basic components, figure 736.
Reservoir, fluid storage, pump, hand, electric, or engine-driven, filter, selector valve, directs fluid, relief valve prevents overpressure, actuator, cylinder piston that does the work.
Hydraulic fluid type.
Small planes usually use mineral-based, like kerosene, dyed for ID. Good lube, stable, crucial to use only the type specified in the POH maintenance manual. Mixing types is a disaster.
Landing gear. Supports a plane on the ground, figure 737.
Wheels most common, but floats or skis too. Usually 3 wheels on small planes.
Two main types, conventional tail wheel and tricycle, figure 738, 739.
Tail wheel, conventional, has main wheels ahead of CG, small wheel at the back. Good prop clearance, good on rough fields, but harder directional control on ground, prone to ground loops, poor forward visibility when taxiing, needs special training. Tricycle gear has nose wheel at the front, main wheels behind CG. Much easier ground handling, better visibility, less likely to ground loop, allows harder braking. Nose wheel can be steerable or free castering.
And gear can be fixed or retractable. Figure 739 again.
Fixed gear is simple, low maintenance, always down. Retractable gear tucks away in flight for less drag, higher speed. More complex, adds weight and maintenance.
Brakes on main wheels.
Yes. Hand or foot pedal operated. Foot pedals usually allow differential braking, left-right independently, for steering help on the ground.
Pressurized aircraft for high-altitude flight. Need pressurization or oxygen?
Both, often. High altitude means efficiency, smoother air, weather avoidance, but air is too thin to breathe, so you pressurize the cabin. Seal the cabin. Pump in compressed air, usually bleed air from turbine engines or maybe from turbochargers on piston planes. An outflow valve regulates the pressure by letting controlled amounts of air leak out. Figure 740 shows a system.
Maintains what kind of cabin altitude?
Typically around 8,000 feet equivalent, even when the plane is way up high. Keeps occupants comfortable and safe from hypoxia without needing masks constantly. Also provides ventilation. But loss of pressure is a serious emergency.
Key terms: aircraft altitude, cabin altitude, differential pressure.
Differential pressure is the difference between inside cabin pressure and outside ambient pressure. The fuselage is built to handle a specific maximum differential. Exceeding it is bad.
How does the control system work?
Cabin pressure regulator controls the outflow valve to maintain the selected cabin altitude, isobaric control, or to limit the differential pressure, differential control. Also, safety valves for overpressure relief, vacuum relief, prevents outside crushing cabin, and dumping pressure quickly if needed.
Instruments for monitoring, figure 742.
Cabin differential pressure gauge, don't exceed max. Cabin altimeter shows effective altitude inside. Cabin rate of climb shows how fast cabin pressure is changing.
Decompression, loss of pressure, explosive versus rapid.
Explosive is instant, 0.5 sec. Very violent, potential lung damage, fog, debris. Rapid is slower, but still fast. Lungs can keep up, but hypoxia is the huge danger in both. Time of useful consciousness drops drastically.
Well, immediate action is crucial.
Oxygen masks on immediately, especially above 35,000 feet. Use 100% oxygen if available. Other risks: bends, decompression sickness, being blown out, wear seatbelts, wind blast, extreme cold. Emergency descent is required. Warning systems alert the crew.
Oxygen systems,
Hey.
right at certain altitudes.
Yes, regulations mandate crew use above 12,500 feet after 30 minutes or immediately above 14,000 foot cabin altitude. All occupants need access above 15,000 feet, but effects felt lower smart to use above 10,000 feet day, 5,000 feet night.
How is oxygen stored and delivered?
Usually high-pressure cylinders, 1-800-2200 psi. Pressure drops with cold temp, not just use. Need pure aviation oxygen. System includes regulator, mask cannula, gauges. Figure 743 shows regulators.
Regulators mix oxygen with cabin air.
Often, yes. Below about 8,000 feet, maybe 100% cabin air. As altitude increases, regulator adds more pure O2, reaching 100% O2 around 34,000 feet. Different types exist.
Big fire hazard with oxygen.
QGE, Oxygen makes things burn fiercely. No oil or grease near O2 equipment. No smoking. Inspect system before flight quantity, leaks, mask condition, clean hands when handling, shut off valves after use.
Delivery methods. Masks versus cannulas, figure 744.
Masks provide better seal, required above 18,000 feet. Crew masks often have mics. Passenger masks simpler. Cannulas go in the nose comfy but less reliable at high altitude, often have flow indicators.
Different system types. Diluter demand, pressure demand, continuous flow, pulse demand, figure 745, 746.
Diluter demand. O2 only on inhale, mixes with air, good to 40,000 feet, pressure demand, like a diluter, but forces O2 in under pressure above 34,000 feet, needed for very high altitudes. Continuous flow, simpler, constant flow, often for packs, uses reservoir bag. Pulse demand, detects inhale, gives O2 puff, very oxygen efficient, often portable. Figure 747 shows a pulse oximeter for checking blood oxygen.
Servicing oxygen needs extreme care.
Absolutely. Strict procedures, outdoors only. Extreme cleanliness, no oil, grease on hands, tools, clothes. 2 people often recommended. Never service during fueling or other ignition risks.
Last topic, anti-ice and D-systems. Critical for flight and icing.
Anti-ice prevents ice, de-ice removes it. Protects wings, tail, props, probes, windshields. Most late GA planes only have pitot heat not certified for flight and icing. Must exit icing immediately if encountered. Check POH.
Airfoil protection, boots or weeping wings, figure 748, 749.
Inflatable boots, figure 748, are common. Rubber sheets on leading edge inflate with air, crack ice off. Cycle them as soon as ice seen. Weeping wing, figure 749, is less common. Oozes antifreeze fluid through tiny holes in leading edge.
Windshield anti-ice.
Alcohol spray system or electric heat embedded in the windshield. Electric heat only in flight usually can cause compass errors.
Propeller anti-ice, figure 750.
Alcohol spray from roots or electric heating elements in boots on the blades. Figure 750. Monitor prop anti-ice ammeter. Check boots pre-flight. Failure can cause imbalanced vibration.
Other heated items.
Pitot static ports, fuel vents, stall warning sensors, often electrically heated. Check operation per POH. Always check systems before expected icing. Not meant for sustained flight and icing in most GA planes.
Okay, the source material wraps up by stressing how vital understanding all these systems is for safe flying and maintenance, and points back to the AFM POH as the ultimate guide for any specific aircraft.
That's the key takeaway. This overview gives you the concepts, but the specifics for the plane you fly are in that book. Manufacturer and owner group websites are great resources too.
Well, that was certainly a deep dive. We covered a huge amount of ground, from engines to electrics to keeping ice off the wings. Hopefully we hit our mission, pulling out the key knowledge to get you informed thoroughly, but without getting totally bogged down.
Yeah, hopefully. And there were some neat things in there, right? Thinking about those old radial engines or how complex yet elegant a constant speed prop governor is.
Absolutely. And things like carb ice, subtle but potentially really dangerous, or how turbos recover energy, how magnetos power themselves.
And the oxygen fire risk, always a good reminder.
It really shows why knowing these systems isn't just for mechanics. For pilots, for anyone serious about aviation, understanding how it all works is fundamental to safety and smart operation.
Couldn't agree more. And for you listening, maybe think about which systems sparked your interest the most, or what questions you still have. There's always more to explore.
And a final thought to leave you with. Aviation tech is always evolving. What's next for these fundamental systems? How might they change? Or think about the connections, how tweaking the fuel system might impact engine cooling, or how electrical loads affect everything else. It's all interconnected, isn't it?
It really is. Fascinating stuff.
Thanks for joining us on The Deep Dive.